The last two new topic for this course is going to be on energy efficiency, and the outline of the lecture for this topic comes from the notes or slides provided that are go along with the textbook Sustainable Energy, Energy Fundamentals and Applications by Surtur Selick, as we've previously been using for some other topics on sustainable energy. Now, energy efficiency is I think it's an approach. It's more of a user-based set of things that we can do to improve how we use energy, not necessarily sustainable sources. But when it comes to this whole idea of sustainability in general, kind of across, all sorts of industries, residences, applying energy efficiency can help us reduce the demand. Then we don't necessarily need as much energy, etc. There's a variety of things that we can do, and this will be a little bit shorter lecture. We'll talk about some things that we can do with respect to buildings, transportation, etc. Um, there's lots of things we can do for energy efficiency, and I think the one main thing that was a big push in recent years is replacing all the lights in house to LED. LED lights use significantly less electricity than incandescent bulbs, but that would be just one approach. So being able to do the same things that we've been used to doing, but at a significantly reduced energy or price load. And ultimately, when it comes to improved efficiency, the bottom line is this will cost us less. And generally, a lot of times people think with, what their personal resources are, and one of those things are, both time and money. And we want to extend our resources, particularly, the time and money as far as possible. There are going to be a lot of things that we can do which would require changes of behavior, and that is a possibility. But again, some of the general focus is to try to think about what the average person would do, and let's make changes you know, that can be realized across large populations. And we'll have some homework related to energy efficiency, and these are going to be a little bit more in lines of, what do you think? What would you propose? What could we do in order to achieve a particular outcome? So again, we'll look at, we'll just talk a little bit about what energy efficiency is. We'll look at how this can be applied to buildings, both, residences, how we can improve things like heating and cooling. We can look at, industrial settings, transportation, etc. As a chemical engineer, a lot of times we do something that's called heat integration, and heat integration is something that is an element of energy efficiency in that we take waste or unused heat from one system and we use it to add heat to another system. So instead of paying for steam all the time, we can take a high pressure steam, go to a low pressure steam, and then use that low pressure steam to do some sort of heating. Maybe we even get out hot water when we condense that steam, and then we could do preheating with those. And each of those systems would require some sort of heat exchange, um, which requires a capital cost but reduces overall lifetime costs and energy use. So as some outcomes from here, we can think about differences between energy conservation and energy efficiency. Conservation is more related to individual human behavior. Efficiency is, doing similar things or doing the same thing for a lower cost. That would be a higher efficiency. We'll look at energy efficiency in buildings, various industry and transportations. We'll talk a little bit about HVAC systems, how we can particularly improve those efficiencies. And again, we think about HVAC, which is your air conditioner. If we just, talk about the idea energy conservation versus energy efficiency, an energy conservation approach could be, when you're not at home, you set your AC to a higher temperature. Like, I don't know, maybe you set it up to 82 because no one's in the house and you don't need to cool it during the day. And then you have it reduce the temperature when you get home and when you're using the house. So that could be an energy conservation. An energy efficiency thing could be, with HVAC systems and cooling systems, the temperature where you're rejecting the heat, which is the outside. You want that temperature, the lower that temperature is, the more efficient your HVAC system is going to be. So there are things that, that we can do. Like, so for example, if you live in a hot climate area, if you have an HVAC system that can reject the heat underground where the temperature is much cooler, you can improve the efficiency. And what that means is it's going to do the same amount of work for a lower energy cost. I will look at a variety of like standards and rating systems that are used for buildings, just so that you're familiar with those. And we've one of the things that we've already talked about before, whether it be for coal or nuclear or geothermal, we've talked about combined heat and power plants, and we'll revisit that from a standpoint of energy efficiency. We'll briefly talk about the importance of energy or industry recycling, and then also discuss the effect of fuel economy on, again, this effective fuel economy. What that does is it costs the more fuel efficient car that you have, the cheaper it's going to cost to run because you will have to buy less gas to go the same amount of distance, and equivalently, if you're using less gas, it'll have lower emissions to the environment. So those benefits come from the improved fuel economy. So again, this idea, and again, energy conservation, and energy efficiency, they're two phrases. They can be used interchangeably, but they're a little bit different. So conservation is an action or a choice to use less energy overall, and so that would be, you're making a choice to use less energy, which means is that you're going to be doing a different amount of work. So this could be a heating, this could be maybe you're walking or riding your bike instead of driving. So you're doing a different amount of work, but you're reducing your energy use. Energy efficiency, again, in energy efficiency, it's an outcome in technologies where you do use less energy to do the same function or do the same job or do the same amount of work. So, and this could be things like, drying clothes. You could imagine using a clothes dryer, putting your clothes in the dryer and using a certain amount of electricity, kilowatt hours to dry the clothes, versus hanging your clothes outside to dry. In the one case, you're not using energy. You're not using any electricity, but it's requiring a little bit of your own, personal manual labor type work. So again, the efficiency, very different, but then there's also an effect on time, quality of life, etc. And again, sometimes this energy efficiency can be a misleading term. Um, it's generally about efficiency is all about output over input. It doesn't matter what the fuel source, whether you're generating your electricity from a renewable source or whether it's from coal or solar. We're getting energy and we're doing work. So in some cases, we might consider something more sustainable, but that's different than in terms of efficiency. Um, Sometimes energy efficiency doesn't really matter, and I think in the case of I don't you might even look at like the case we looked at with clothes drying, like how much energy are the clothes receiving from radiation energy from the sun? I mean, within a particular area, there's a whole lot of energy raining down, and how long does it take? I mean, that might seem like it's not a very efficient process, but it's a cheap process. We might have low efficiency processes where we get, essentially cheap and free energy. And some of that within the case of when we looked at geothermal and we saw Carnot efficiencies on the order of 15 to 25% rather than, something like nuclear power that has efficiencies, closer to 30 or 40%. The nuclear might be more efficient, but the geothermal is we're free fuel. So efficiency isn't really always the end all metric that's, we're going to think the most efficient. We want to look at, what's the overall cost, and oftentimes cost and efficiency are related, but not always. And we can also, there's a variety of things we can do to improve the energy efficiency of, buildings, companies, vehicles, electric devices, etc. Even when it comes to, building the orientation of the building with respect to the rising and the setting of the sun can affect the energy use. We can put, heating walls on buildings that are in colder climates, or we can put more glass. And there are various things can be done in terms of how a building is built in order to improve the overall efficiency of the building. So again, the buildings are a big thing that use energy. And if we look at this globally, they amount to really high building use, and there's a lot of work that's going on in order to increase the efficiency of buildings. And a lot of, especially in cities, they're trying to purposely design, their cities or their buildings in order to minimize the electricity costs. And some of these things could be things where you have glass that's coated with a dark material to reflect some of the sunlight so that the building doesn't absorb as much. There are things like some places across the world are either building plants or moss on the side of their buildings to reject or so that the building doesn't absorb so much of the sun's heat. There are things like, so again, there are different terms can be used like green building, sustainable, smart, net zero. A net zero building might be considered to be a building that doesn't have any net carbon emissions. A smart building would be something that uses either artificial intelligence or controllers and programs to set the building under certain conditions in order to minimize the overall use of energy in order to achieve a particular goal or a particular function. Again, if the function of a smart system is to keep it at a comfortable climate while people are there, then the climate when people aren't there doesn't matter. So the smart building can make adjustments there. And even so, there are buildings and systems where, lights become automated. Someone walks in and automatically turns on the light. Someone walks out, doesn't necessarily turn it off right away, or maybe it turns it off when there's not someone that's detected in the room. So these are approaches that can decrease energy uses, and as we kind of move forward, um, incorporating new systems with these will decrease energy requirements in the long term. So when we're building buildings, there's a variety of things to consider, and obviously, the location and the weather are going to be some important things. The conformation or the size of the building, or what are the needs of the building and its particular job. Equipment and devices. So what are we doing inside the building, and then also occupancy. Like, are there people, and which areas are the people in, or what does the climate necessarily need to be for equipment or devices? Um, Kind of some of the low-hanging fruit are really the easy things to improve building efficiency, and these are things you're probably already familiar with avoiding any air leaks and making sure that the buildings have good insulation. So insulation is a huge insulation, and how it's set up into buildings is a huge factor that affects efficiency. A lot of times in residences and commercial buildings, insulation can be blown in certain ways, and while that can be generally good, going in and doing secondary insulation can improve overall uses, especially in places that are really hot or really cool. Windows are a huge source of efficiency or inefficiency for buildings. Older buildings that might only have single pane versus newer buildings with double or other types of windows, potentially vacuum sealed, and systems that don't require as much of the energy from the sun absorbing into the building. High performance lighting, or in other words, LEDs versus incandescent. And then some other things. So we can use passive solar designs for heating and cooling, and this can be strictly just only orientation of the building. There are building materials that, if you live in a cooler climate, buildings can be built with walls that are made to absorb the heat, which will reduce the overall heating costs in the winter time. And again, the orientation of the building would have to be such that the heating wall is facing towards the sun. We have passive solar systems which can be used for both heating and cooling. So again, a passive solar system like we looked at in solar, might have some tubes that have water flowing through them that get heated with the thermal energy, and then those go through either radiator systems or hot water tanks within the house to provide either heating for the home or hot water for the hot water usage. And then also things like green roofs. So a lot of roofs have dark tile for aesthetic reasons, but if we moved away from dark tiles, even lighter tiles, or even natural or grass or plants, or if we can put other sorts of natural vegetation up on roofs, it can very much improve the efficiency. Along those lines, even having large trees, houses under large trees where the sun doesn't necessarily get through can help cool houses in places that get a lot of sun. Okay, so when it comes to the central heating and cooling, there are many options, and particularly when it comes to cooling, a common one is central cooling. We can also have AC per room, and this could be window or wall heaters. There's cooling called ductless mini splits, where it has a mounted duct on the wall that's connected to the outside component, and then we can also have evaporative coolers. And depending on which one of these systems, it can affect the both. I mean, they're going to cost different, and they're going to affect efficiencies. And one of the cheapest methods um, for doing cooling, could either be room, because again, room is small, it's only doing, but to do room cooling on all the rooms, then again would become expensive. Evaporative coolers is a really cheap way to keep houses cool, and this requires the addition of water. So it uses the evaporation of water to absorb heat from the building. But this has limitations. This can only be done in places that have very this can only be done in places that have very low humidity, because again, the water has to evaporate, and so based on how much water can go into the air, there'll be a certain temperature related to the dew point, and that can tell you the type of cooling that can be achieved based on the humidity that you're accessible to. Central air is the most common. Um, Again, these are generally a little bit more expensive. Many houses and homes are built with them currently. They're often quiet, and they can have a lot of control components to them as well. With central air, we have ducts that flow through the building, and you have receivers of the air inside the building and delivers of the cooled air to the building. And then in the air conditioning component, which we looked at a little bit briefly, there needs to be a place that we reject the heat, and that's what that would be outside. So the outside temperature is used um, is to reject the heat, um, and which is the case in pretty much, yeah, all of these type systems, even the ductless mini split. This would have an individual duct that's installed in a particular room, and these are very efficient, but they end up costing quite a bit. One of the things, so because again, when we think about AC, most modern homes use this idea of central type AC. And again, in these systems, we can set the temperature inside, and the temperature outside is where the heat is rejected. Um, Again, the lower that we have access to on the outside temperature, the more efficient these systems can be. One of the ways that we can improve efficiencies on buildings is by rejecting the heat to a temperature underground. So if we could employ some sort of dig a hole and put the AC outlet receiver or outlet component um, that's underground, that has access to the temperature underground, these the amount of work that we need to do for air conditioning a building would be significantly reduced. And so these are some things that people are working on. The problem with that, they have a higher capital cost, but they save a lot of money. Again, ideas for heating buildings are shown here. A lot of times people who have natural gas will have furnaces. And again, the furnace will, turn on and off when needed, and it will burn natural gas to heat up air, and it'll deliver that air through the house. So a lot of times if you have central AC and you have natural gas heating, you probably have something like a furnace. Otherwise, you would have something like a heat pump to take the air from the outside, warm it up, um, and deliver that to the house. Again, these would be the common things that you do, but the heat pump can be fairly efficient, but they are generally a little bit more expensive. Active solar heating is a very inexpensive way in terms of operationally in order to heat a building. Again, this would require these panels that are placed, and they would, really only be able to heat water when we have access to the sun. So when the sun is shining, it's going to warm up the water, heat up the water, be stored, and then this hot water can be used for showers or dishes, or it can be flown through radiators to heat up the building. And then we also have electric heating, which is, like resistive type heating. And again, these are, either for something that would be required for a large house, this would be very expensive. But again, they're fairly efficient in terms of operation. All right, so we can go through some calculations to figure out how much heating or how much cooling we need on a certain, and then this can be converted to the work required to do the particular job. So when we have things like, cooling, we have this idea of conduction, where conduction is UA delta T. So the amount of cooling that would be required on a building would be related to the heat transfer coefficient in the area and then the delta T. So the delta T would be, the difference in the temperature outside the house versus inside the house. Again, if we're cooling, the inside of the house is probably around 70, outside of the house maybe might be 85. And then again, the U and the A, so the A would be the area for heat transfer. So this would be like how big the walls are, ceilings, how big the house in general. And then this U would be the heat transfer coefficient. And the heat transfer coefficient would be, the average rate at which heat moves through certain walls. And obviously, heat will move faster through things like windows and cracks than it does through cement. We can also have radiation through fenestrations, and these would just be general openings in the house. And again, this is calculated based on what's called a solar heat gain. Again, the surface area of the fenestration or the opening, and then the shading coefficient. So these would be things that can be calculated if what sort of heat gain you would expect through a certain opening. And then again, we have ventilation and we have infiltration. And again, ventilation, this can be sensible and thermal heat. And again, the sensible heat is going to be the amount of flow of the air that's being vented or flowing in times the temperature difference. So this is based on the rate of flow of a mass into a building. And then the latent heat from ventilation or infiltration can be related to a phase change. So what is and this could be related to, maybe water evaporating, perhaps. We would have to require absorbing water or water condensing. So during when we're heating, we can have heat losses, and again, these are going to be fairly similar. The amount of the heat loss is just going to be based on the heat transfer coefficient in the area of the building, and then whatever the difference is through which the heat is flowing. So if we're keeping our house around 70 in an environment where the temperature outside's 40, and again, we're talking about in terms of Fahrenheit, we can, based on the heat transfer coefficient in the area of the building, we can get an idea about the heat. So obviously, the lower the temperature difference, the less heat losses or heating required would be for that building. And then also, again, like before, we have infiltration losses based on the flow of air into, or the flow of something, probably air into or out of the building through different avenues. And that's going to be based on the mass flow rate of the air and, again, the temperature difference as well. Lighting and appliances, these have, again, we'll talk about these in terms of energy efficiency. When it comes to things like energy conservation, I think some of the general things are just like turn off the lights when you're not using them. I don't view that as conservation. I just view that as practical. Like leaving lights on when you're not viewing them is not is the opposite of conserving, which is wasting, I think. But then we can consider, changing how we do things. Like, so, making sure that your dishwasher is full before you run the dishwasher. If you run the dishwasher half full, I mean, it's only half efficient. Same thing with clothes, same things with, clothes dryer. So making sure we're doing, if not just doing like washing a few clothing items at a time, doing a reasonable load that gets the job done. Really, what's the largest load that can get the same job done? Again, so now when it comes to lighting, again, lighting is measured so the amount of light is measured in like lumen output. And so the amount of light needed, which is luminous flux, is measured in this terms of lumens. Right? This could be also called brightness. And again, so this efficiency is again, it's going to be related to the ratio of the lumen output over the power input. So how much power do we have to put in to get an equivalent or to get a certain lumen out? So if it took us, or let's see, if we use SI units and let's just say our input was 1 and our output was 2, the efficiency would be 2. Okay. So again, the lumen, okay, this is, so the efficiency value, again, this is not a percentage, it would be lumen per watt. And if we wanted to get this in terms of energy, in terms of a percentage, we could look at equivalent light power needed, and that would be lumen output over efficiency. This plot over here shows kind of general usage, energy usage in general in standard homes. Across the US. So looking at clothes dryer uses the most electricity, clothes washer, the next most, or refrigerator and the clothes washer, and then dishwasher over here. And so again, we can, in terms of efficiency, it would be, what is the energy input of these units? What does it require to do the job? In terms of energy, if we're trying to conserve energy, we might do fewer dishwasher loads. We might, maybe wear our clothes that aren't not wash all our clothes, just wash the dirty clothes, for example. In terms of refrigerator, taking care of how you open and close and what your refrigerator settings are. Okay, so this example right here, again, so for energy efficiency, I think it's important to think about what are some things that we can do, or how can we improve or decrease the amount of energy that it takes us to do the same things that we're currently doing. And then, as we continue to go further, we can think about what are all the things that we're doing necessary. Can we do fewer things and still have the same quality of life? I think that's the overall goal, is that we have continue to increase quality of life, decrease the amount of resources required to achieve that goal. Okay, so let's consider a domestic refrigerator that has a cooling capacity of 420 watts and a compressor power rating of 150 watts. The cooling capacity is determined by the heat gain of the refrigerator under steady state conditions. Determine a couple of things: coefficient of performance, annual cost given the information, and then what is it? Annual cost in electricity. Oh, if the overall heat transfer coefficient is reduced by 10%, so that would be improved efficiency. Okay, so the coefficient of performance of a cooling system is simply the ratio of the amount of cooling done versus the work that goes into the compressor. And so again, we're given those. So cooling capacity, that's the max cooling it can do, 420 over 150 watts, so 2.8. Annual cost of electricity. Okay, this is going to be based on the work this is the work that's being done by the compressor, based on how long is it working for, based on what's the cost per energy. Okay, so the annual operating, we're told it's run for 14 hours a day. So 14 hours a day times 365 days a year. And so so okay, so here we get hours. So this over here, watts, um, hours, so we need hour, year, etc. So we're looking at getting the units of dollars per year. So again, the watt in kilowatts cancel or unit exchange over here. So now we see the whole unit thing. So we have the time, operating time, we have the unit price, and then we have the work of the compressor. So essentially the assumption here is it's running at 14 hours a day and it's running at its power rating. Um, and that just might be, and you might be able to consider these refrigerators may just turn on all the way or may turn off or may run at certain, levels of their power rating of performance. And then it would just have to be, calculated accordingly. So this is just saying it's either on or it's off. And so it's running for 14 hours at 150 watts, 14 hours a day, 360 days a year, because we're looking at the annual cost. Electricity costs 7 point or was it 0.076, so yeah, dollars 7.6 cents a kilowatt hour. That's fairly low, I think, a little bit low, but not too bad. But anyway, so this we do unit conversion, we get about 58, 27, 25 per year. Now the next question is a little bit tougher. So now what this is saying is the overall heat transfer coefficient is reduced by 10%. So we can look at this two ways. Is we can what that means is we can do the same amount of work. We can do the same amount of cooling for 10% less work. Okay, so it costs us or we can consider that we're instead of running the compressor all the time in the previous case, we now only need to run the compressor at 90% of the time that we did in the previous case. Okay, so in order if the heat transfer rate is 10% lower, we only have to do 10% as much cooling. The compressor only needs to be on 10% as much, or 10% less than previously. So if the compressor only has to be on for 10% less than previously, then we know our current cost should be 90% of what it was previously. And again, this equation, that's what this shows right here. So they don't really talk about how they reduce the U value by 10%, but I walked through it with you a little bit. You could calculate, again, you would need to do the amount of cooling, this refrigerator can do 420 watts of cooling at 150 watts. So then we look at how much cooling we can get 10% more cooling because we lose 10% less heat. And for the 150 watts, we get that much more cooling, which again, when it looks in terms of annual usage, that means we're running the compressor that fewer times to do the same amount of. Okay, across the world, there's a variety of different standards, and I guess these you can just be familiar with. In the US, you have Energy Star and LEED, and other places there are these other types of codes. But again, the codes can be important. It can tell you about the energy use, and so in order to be a certain rating, it has to be a certain energy use, and sometimes you can get tax credits or subsidies for using these energy type of a system. Some systems where energy efficiency is extremely important are shown here. Again, any sort of, petrochemical process, paper making process, all these pharmaceuticals, we're always trying to improve the efficiency of that because that allows us to make the same thing at a significantly reduced cost. And these are industries that make a lot of things. So again, in terms of energy efficiency, the one way that, if we think about conventional way or a single way of using the fuel, we could take the fuel, we could burn it in an engine. The steam could run the turbine, the steam could run the turbine, and then the hot gas would just be rejected to the environment. And so we would generate electricity and produce our power. In a combined heating system now, instead of just rejecting this heat to the environment, we can use this heat we can recover this heat to do some amount of work. And so if we have a heat exchanger between the waste heat from here and the water, we can either produce steam, depending on what the pressure and temperature differences are, or hot water. And this hot water can be used for cooling the building. So the combined heating power system is an example of improved efficiency by using this, this hot gases or this rejected energy from the heat engine process in order, or from the engine process to do some sort of heating work. And again, another example, in this case right here, we looked at we're burning a fuel in an engine, and in this case right here, we're looking at you know reacting or burning a fuel to produce steam. The steam is going to run the turbine, spin the generator, produce electricity, like it did before. The low pressure, low temperature steam, it can be used directly as steam or hot water. And that can be used for heating, cooling within a building, or etc. So this low pressure steam has a variety of uses, or it can just be used for heating. For efficiency, when it comes to transportation, there's a lot of things that we can think about. The shape of a car is a huge thing, but unfortunately, the most efficient car in terms of aerodynamics is very ugly. To improve, again, what the overall goal is, we do the same amount of work, we get the same amount of distance, transport the same number of people for lower cost. And so that's the idea for energy efficiency here. So again, fuel standards are one of the ways to get there. So cars and trucks having improved gas miles standards. And again, these are different for cars and trucks because trucks generally have a different purpose of doing some work rather than just transporting people. We can also think about improving bicycle and pedestrian and, potentially public transportation, discouraging the use of automobiles. What do you think about that? Is that energy efficiency? I think this falls more in energy conservation because you're changing people's behavior. You're not allowing them to drive through certain areas. Again, public transport's good in terms of efficiency. And then some other things we can look at across the board are things like rail transport, maritime transport through the water as ways to potentially, move people around for less energy. Here's some information about fuel efficiency, and again, this is history of real world fuel economy and CO2 emissions. So again, and maybe average fuel economy going back to 1975 has increased, generally over the years, which has led to a reduction in the CO2 output because we're moving the same, or we're actually moving more distances now than we did previously. But it doesn't require as much CO2 emissions per fuel source. Here's a sticker again that the Environment EPA DOT has fuel ratings, and it gives miles per gallon. This is a miles per gallon equivalent. It looks like this might be an electric vehicle because it's giving in mile per hour equivalent. This is telling you how much you'll save in fuel over the 5 years. This could be a potentially misleading number because while you don't have to pay for gas for electric vehicles, you do have to pay for electricity. So one of the things I might ask you to do for homework is look at what is the difference in cost if you are charging your car versus paying for gas to do the same job. That will make for a good question. So here's in terms of, for electric vehicle or transportation, I guess this is going from St. Louis to Chicago. How far would this be? So again, this is looking for things like charging stations along the route. So if we look at this route, we would know that we can go drive between here and there we'd see a gas station, every couple of miles. But there are various other types of electric charging stations. Potentially can't exactly tell what these are from this plot, but various things you can tell based on the type of fuel that you have, how you would need to recharge, between these two locations. And electric charging stations are becoming a little bit more common, so it's now possible to drive these routes with electric vehicles, but in some cases may need to plan your trip a little bit. So here's a fuel economy comparison for two different vehicles, and it's based on the 2021 economy guide. And I think in here we're looking at a variety of different cars that have miles per gallon ratings on the city and also highway. And the analysis is going to assume 15,000 miles driven per year, with 55% of these miles highway and then 45%, or 55 city, 45% driving, and then assuming a cost of gas. And so we'll just compare each one of these types of systems to determine the combined fuel economy. So the couple of ways you can do this problem is we can figure out the cost of driving city miles and highway miles independently, right? So we would just take 55% of 15,000 miles, which was about 8,000 miles, and then take 8,000 miles and use that with the miles per gallon in the city to get the gallons. And then we do the same thing, the 45% of 15,000, divide that by miles per gallon to get gallons, and then we'll have the total gallons and get the cost. Or we can get an average. What is a weighted average mile per gallon based on this driving? And that's what we're going to do first, and then we'll calculate the average. So the miles per gallon, and again, we just have to do the reciprocal of the sum of the reciprocal, because essentially what we need to do is we need to get the combined mile per gallon rating. It's not going to be mile per gallon multiplied by 55%. Okay, let me go back. It's not just going to be this MPG multiplied by 55% and this number multiplied by 45%, because the units don't work. Okay, so we need to kind of take what is the total. We can look at what are the total miles driven, and then we need to look at what is the total gallons driven, and then we get the gallons per city, we get the gallons per highway, and if we simplify it down, it gives us to this equation right here. So this combined miles per gallon is a weighted miles per gallon based on city and highway. Again, the miles per gallon on the highway is significantly higher. Anyways, where we going? Okay, then the annual cost is we just have the annual miles divided by the combined MPG, and then we get the dollars per year. And if we look at these different cars, again, mile per rating, the highest mile per gallon car costs about $1,800 a year, whereas the lowest MPG, $2,800 per year. But again, would you rather drive a 8-cylinder Corvette or the Mini Cooper? I don't know. But anyways, not a huge cost in difference, especially based on the cost of the car. But these are things that will affect the amount of resources that you have for other things. So again, energy conservation means saving by doing things differently. Energy efficiency is doing the same thing for a reduced cost of electricity. We can improve a huge cost of energy use is heating and cooling, and this can be significantly improved with insulation, energy efficient appliances. Again, where we're getting our initial heat from and where we're rejecting our heat to. Again, in industry, we can do the combined heat and power systems and look at heat integration to make sure that most of the energy that we are getting from the fuel source will go towards a use. And then there's a variety of things that we can do for transportation. So I'm going to give you a couple things to think about. Just kind of looking at your opinion. What would you do? How could we make some improvements going forward? And again, this is both in terms of energy conservation. So how can we affect human behavior in a realistic way? And also energy efficiency. What are some things that engineers can do, or where should we focus to improve efficiency in systems?